All right, the time has come. I think we can start. It's 10 a.m. Hello everyone, and welcome to today's webinar about developing large language models for low resource languages with a special focus on Slovene. My name is Tomáš Kolarik, and I'm part of the Slovak National Competence Center for HPC, and I'll be moderating today's session. This webinar is part of our ongoing series on LLMs for low resource languages, and today we are excited to take a closer look at the GAMS, which stands for Generative Model for Slovene. Our speaker is Domen Vreš from the University of Ljubljana, Faculty of Computer and Information Science. After the presentation, we'll open the floor for Q&A, so feel free to ask your question directly to the speaker, or feel free to post them in the chat section in the meantime. Domen, thank you for joining us. The floor is yours.
Thank you for the introduction. I hope that you can see my slides. Okay, so let me start by introducing myself. I am Domen Vreš. I come from University of Ljubljana, Faculty of Computer and Information Science. And we are training a Slovene large language model called GAMS. Okay, so how did we come up with this idea to train our own LLM? Well, we have this research project Poemo at our university, and the goal of this project is to firstly develop an open source generative large language model for Slovene. This is currently a still ongoing project, so it's between years 2023 and 2026. And as a part of the project, we are also collecting Slovene training data. This is actually the web page of the project, poemo.c, where we are asking the general public, so Slovenian people, to submit their texts. So far I can say that we collected more than 30 million words from the general public, but of course, this is far from enough to train any model, and we are kind of more looking towards getting the data from bigger institutions such as National Library, National Television, journals, and so on. And yeah, we are already received data from, for example, from National Library, and it's a significantly larger amount. And as a part of the project, we are also aiming to adapt our LLM for specific use cases. This is done by the company, so we also have 4 companies on the project, so they will adapt it for the domain of their work. For example, we have digital humanities, so we have one company that is working with these national museums, and they want to optimize the search and descriptions of the articles in the museum. Then we have the company that's working in medicine. Of course, they want to automate the bureaucracy for the doctors, and so on. Okay, let me start by this motivation. Why do we even need an open source model for Slovene? Because this is a question we get often. Of course, we have ChatGPT, we have Gemini, we have many other successful commercial LLMs. But as you may be aware, the problem with such models is that you need to submit your data to their API. So you're sending your data to an external server, and this is, of course, not feasible when you're dealing with sensitive data such as healthcare information, so law data, and so on. And that's where the open source models come in. Like the most famous representatives are Llama and Gemma, and you can have those models on premise, so you can download them, you can run them locally. But the problem with them is that they do not really speak smaller languages, or let's say less resource languages well. So one example is, of course, Slovene as well. And even more, maybe that they do not really understand the Slovene culture. Because I can say that the Gemma 3 is now quite efficient in Slovene already, but yeah, there are areas where it still lacks. And to really show why that they don't understand the Slovene culture, I have this nice example that I always show. So first, disclaimer: I asked this Mistral Nemo Minitron model like more than a year ago, and of course, you know that year is ancient history in the area of LLMs, but nonetheless, I asked it in Slovene to give me a recipe for spaghetti bolognese. And okay, I'm not going to translate now this response, but the point is the ingredients that it suggested for the spaghetti was 500 grams of gibanica. And you probably don't know, but we have gibanica here on the left, and this is traditional Slovene dessert, and of course does not have a place in spaghetti, but because the model knew that gibanica is somehow related to Slovene, it included it. So this is really the motivation that shows that models do not understand Slovene culture. Okay, so now that we have our motivation, we are decided to train our open source model. How do we approach that? So the basis behind the LLM training is we train the model to predict the next token. So as you may imagine, the neural network cannot work directly with texts, and that's why we first tokenize the text. Basically, we split it into discrete units called tokens. We can think of tokens as an approximation for words. I have one example here. So, for example, the string tokenization example would split into 3 tokens. And this is also the sign that there is a space between 2 words. Sorry, it will be split into 4 tokens because we also have a full stop at the end. And yeah, as I mentioned before, what are we doing? We are just training the model to predict the next token. So basically, here we would have, for example, token on the input tokens tokenization, and then we want the model to predict example. And also one important parameter that you might know about the models or hear about it is the context window. And this means that what is the maximum number of tokens that we can fit into the model. So for example, the Gemini and I think that GPT now as well have like 1 million token context window. So basically we can put around 1 million tokens in it. The latest open source model will have around 128,000 tokens. We are currently with GAMS in 8,000 tokens context window, which is enough for a lot of use cases. But if you're processing longer documents, then it becomes problematic. But yeah, we will increase it in the near future as well. Okay, and how does the usual training pipeline looks? First, we have a pre-training phase. There we are just teaching the model to speak the language, to build its internal knowledge. And yeah, this is basically just the next token prediction phase. We are training the model on a large amount of data sets, a large amount of training data. And of course, because of this large amount of data, we also need a large amount of resources. When we finish this phase, the model knows the language, it has some knowledge, but it cannot really respond to our prompts well. So it would not be like the ChatGPT. And that's why we need to tune the model for answering such prompts. And this is done in the supervised fine-tuning phase. Here the model is given a prompt and is actually trained to produce the response. And for this phase, we actually need a significantly less resources because we need significantly less amount of data, because now the model already knows the language. We just need to tune the format of its responses. And then usually followed by this supervised fine-tuning phase, or even can be combined with this phase, or it can be or it can come before and then followed by supervised fine tuning and then by preference alignment. So these two phases now are kind of changing in the recent past. So yeah, the last phase is then human preference alignment, and the approach of this phase is that when we now train the model for answering the prompts, we can still adapt it so it suits the human preference better. So for example, it can produce shorter responses or longer responses if we want. It can be tuned for safety, so it does not respond to certain prompts. It can be tuned to reduce the amount of hallucinations and so on. And historically, this was done by reinforcement learning with human feedback. But this is costly, both in terms of data and resources, and that means that also the cheaper alternatives exist. For example, one is NVIDIA's TRLM, then we have direct preference optimization. GERPO is also famous now, so the method used by DeepSeek, and so on. Okay, now to go into the pre-training. So why do we need what I mean by large amount of data? For example, when we started with our project, Llama 2 was released, and they trained Llama 2 on 2 trillion tokens. So, for example, that we can imagine how much of quantity is that. The whole English Wikipedia, which is, I would say, quite a large resource, has only 5 billion words. So by around factor of, let's say, 1,000 or 500 times less than it was this pre-training corpora for just Llama 2. And they realized that even after the 2 trillion tokens, the model was still learning. So that's why they increased the training corpus for the Llama 3 up to 15 trillion tokens, and that's and then even for Llama 4 to up to 30 trillion tokens, which is really really a lot of data. So for example, for Slovene, when we started our project, we had 9 billion words, or around, let's say, 12 billion tokens. So we are kind of by a factor of 2,000 behind what these models were trained on. Now I can say that through our data collection, we improved these numbers, and we are now approaching 40 billion words. Still, by quite a significant factor smaller than the big guys, but it means that we can effectively fine-tune the models for Slovenian. By that, I mean that we take an existing models and continually pre-train them on Slovene. So the idea here is the models have already their knowledge. They are fluent in English. They even saw some Slovene. So as I mentioned, in the case of Gemma, it can really speak now good Slovene. But if we add more data, we can. So if we add more Slovene data, we can now adapt them for Slovene culture and for Slovene language. And that's how we come to our GAMS 9B model. So this is a generative model for Slovene. Why name GAMS? Because we went into this direction of animals. So we had llama, alpaca, and so on. And GAMS in Slovene actually means chamis. So it's an animal that lives in Slovene Alps. And we thought that it would be a nice idea to name it that way. And the current version that is published on our Hugging Face, here is also the link. It was first continually pre-trained on 15 billion tokens, so really small amount of data. Now I can mention that we are preparing next training stage on 150 billion tokens, which will be significantly more. But even these 15 billion tokens already have for the model that it speaks really better Slovene than Gemma 2 spoke before. So why did we choose Gemma 2? This was the idea for this came a year ago, where when the Gemma 2 was kind of the best of the open source models in this 10 billion parameter range. So it was best for Slovene. Well, then, of course, Google released also Gemma 3. They actually released it on the same day that we released our GAMS model. And now we are also thinking about maybe switching to Gemma 3 for the next generation. I also can mention that our model can be tested for free at our data collection website. Here is also the chat interface for the model. I can mention here that, of course, it is tuned mostly for Slovene, but it has also knowledge from other languages. It was trained for English as well, for Croatian, Bosnian, and Serbian, but it can have some knowledge of other languages that it inherited from the Gemma 2. Okay, and actually, how did we approach our continual pre-training? We actually did 2 stages. And in the first stage that I call parallel alignment, we actually try to explicitly align English and Slovene languages. We did that by using parallel English and Slovene corpora. One that is really good for that is the translation corpus from the European Commission called Digiti. We also included abstracts from final thesis from Slovene faculties, because abstracts of Slovene thesis needs to be in English as well, and of course abstracts of English thesis needs to be in Slovene as well, so you have kind of natural parallel data there. There also exists parallel web corpus for Slovene named Mokopku, and we also included machine translation of CC News, but this machine translation is quite questionable. I'll talk more about machine translations at the end. And this corpora included 1.9 billion tokens. But it actually helped because it kind of boosted this alignment. So the model could transfer some knowledge from English to Slovene. This was then followed by high quality corpora. So we included, of course, Wikipedia. We here included also English Wikipedia in order to keep some of the original models training distribution, because all of these open source models are also trained on Wikipedia, and you don't want to drift too far away from the original distribution. We included corpus of academic Slovene, so these are the bachelor, master, and PhD thesis from Slovenian universities, and also collection of curated Slovene corpora that already existed before our project. So web crawls, parliamentary data, some textbooks as well, some books as well, and so on. Here I need to mention that we excluded some subcorpora such as tweets and comments on, for example, news news forums. Because this content is quite questionable, both in terms of content and the forum. And because of the similarity of languages, we also included Croatian, Bosnian, and Serbian. Here it was included in terms of Wikipedia. And the second stage was consisted out of 13.6 billion tokens. Okay, from pre-training then to supervised fine-tuning. As I mentioned before, in this stage, we train the model to follow a given instruction, and this is usually proposed using some chat template or prompt template. This is an example of such template from Stanford Alpaca. So the model needs to know where is the instruction, where is the response phase. And basically, in this phase, the model is, again, trained only to predict the next token. But the catch here is that it is trained only on a response. So the loss is masked for the instruction part. And one thing here is as well that, for example, with this Stanford Alpaca, we can see that the instruction and response are separated by some predefined string. This can be quite problematic for example, for prompt injection and so on. So the best practice that is used now is that they're actually separated by some special tokens. And for example, we used for GAMS or GEMAS template, which includes start of turn and end of turn tokens. And that's how the model separates between, for example, user and the assistant. Yeah, and how does the SFT datasets looks like? Of course, there is an instruction and there is an expected output. Here is an example of a self-instruct star coder dataset from Hugging Face. Okay, so how did we approach? This stage in terms of data? We first synthetically generated our GAMS instruct generative dataset. General dataset. This was generated by the self-instruct method using GPT form. So if you're not familiar with self-instruct method, the approach is you first ask the model to generate the instruction, then you ask the model, for example, to generate an input, and at the end you combine the instruction and input and ask the model again to generate the output. So the whole data set is synthetically generated. First, we generated 20,000 examples, then they were manually inspected. So from those, around 7,000 were annotated as OK and were publicly released. What is the problem with such data set? Well, of course, we have hallucinations. And the funny part is that, the most problematic part is the generation of output. So the GPT kind of failed to generate the output on, or let's say correct output for the instruction that it generated for himself. And another problem was also biases, because when you are doing this self-instruct approach, you are actually sampling data from your current distribution. So you give this data as a few shot examples to the model. And the funny thing that happened here is that somehow a lot of photosynthesis were included in this early stage, and by the sampling approach, it was probably also included in a lot of few shot examples, and that's why I think that around out of 20,000 examples, we had around 5,000 examples about photosynthesis. And of course, you want balanced topics in your data set. That's why we are working now on a newer version of this data set, but I'll talk more about that later. So, but the idea here is that we generate this data in more balanced fashion. Okay, but we then had this data set, but our idea is that we want more and more diverse data. So we also included our other data sets in our SFT mix. We had two GAMS instruct data sets that were provided by our project partners. So one is for the digital humanities and the other is for medicine. And this one, the DH data set, was completely created by humans. So the prompts, the responses were written by humans, and it contains around 10K examples. And it also includes sources from where, for example, you could find this answer. So this is kind of nice data set. And the other one is about medicine. This was mostly collected by the database of medications, and it includes prompts and outputs about the use of these medications, because the company that created this is more interested in such use case. We also included some translation examples. So we added both English to Slovene and Slovene to English translations. This was sentence, but this was sentence-based translation. So in the future, I would like to have, for example, longer examples. And we also included public AIA dataset. This is so we included only English and Serbian parts. So this is basically also generated by some larger models, but the nice case is that they tend to hallucinate less in English. We also included some solved problems from the national math competitions, but they were like around, I think, 100 or 200 problems. At the end, it resulted in 25,000 examples. And as a result, the model learned to respond to the prompts, but it likes to produce short answers. We now find the solutions for that as well. I'll also mention it later. But now let me just go quickly through the more technical details of our training. So in terms of framework, the main work was done using NVIDIA's NeMo 2.0 framework. Why is this framework good? Because it enables efficient scaling across multiple GPUs, and it's kind of easy to, once you have your training working on, for example, on a single node, it is easy to scale it across the multiple nodes. And we use it to pre-train our models, and we also use it in the supervised fine-tuning phase of the 27 billion model. Maybe the problem of this framework is that it's a bit complex and it's kind of difficult to start with, but once you get used to it, you can work with it efficiently. Now I need to say that 2.0 framework is also much nicer than 1.0, because in 1.0 you were mostly working with YAML configs, and then you had to include this into your training scripts and so on. Now basically everything can be handled from the Python code. We are also using Hugging Face Transformers library in combination with DeepSpeed to train the SFT models for the 2 billion and 9 billion models. And yeah, we were using weights and biases for logging. In terms of the technical challenges, one is, of course, the memory requirements of such models. So here in this slide, all the numbers are given in 16-bit precision. We were not using 8-bit at any stage, because I still believe that our models are small enough for them to be trained to be efficient in 16-bit. And for example, here, even for just storing the model weights, the gradients and the optimizer weights, you need 16 bytes times model size. So in terms of times model parameters. And this means that even for the 9 billion model, you already need 144 gigabytes of GPU RAM only for this storage part. And then, of course, when you're doing forward and backward pass, you also need to store activations and so on. And this is more difficult to compute. So I'll just give the number. So for example, for GAMS 9B, we would need approximately 200 gigabytes of RAM just for the activations. And altogether, it comes to around 350 gigabytes of RAM. Now, one trick to reduce this activations memory is to use activation checkpointing or recomputation. I will explain it shortly. So, and this trick actually reduces the activation memory needed from, for example, for the square root of the number. And another issue is also communication between nodes, because we were using the Euro HPC architecture, and because the model is split across multiple GPUs, the communication between these GPUs needs to be fast, because activations are continuously exchanged, and of course gradients as well. And another caveat here is also that the communication needs to be stable. Otherwise, the Nickel library, which handles the communication, can crash, and it stops the training. Okay, I already started with the hardware. So what we actually using here, we're working with European high-performance computing, and yeah, we are here thankful to SLINK, which is Slovenian supercomputer organization, because first we got the access to our supercomputer Vega through our through our project application. But then when we realized that maybe Vega will be too small for us, we also get the resources of Slovene organization on European supercomputer Leonardo. Additionally, we are using also our faculties cluster. It is not suitable for large-scale training because we don't have as many GPUs. But for example, for some supervised fine-tuning and stuff like that, and for the evaluation, it is very useful because we actually have really capable GPUs. And of course, all these HPC clusters use Slurm scheduler, which can also pose another challenge when you try to run your job across multiple nodes. Okay, but what is the actual architecture that we are speaking about? So, for example, Vega has 60 nodes, and every node has 4 A100 GPUs. So in total, it has 240 GPUs. But the problem here for us is that it only has 40 gigabytes of VRAM per GPU. So it actually has only 160 gigabytes per node. And as if you recall from before, I mentioned that we would actually need 350 gigabytes, or if we reduce the activation resources using activation recomputation, the requirement is around 200 gigabytes. And this means that the model cannot fit, or one model instance during the training cannot fit on a single node. And why is that problematic? Because the internode connection, so the connection between nodes, is using InfiniBand switches, and it has 2 times 200 gigabits per second, while the intranode connection, so the GPUs on a single node, can communicate with 600 gigabytes per second, so significantly faster. And this means that all these activations can be communicated in a faster way. And if you have a single instance on a single node, this means that between nodes you only need to communicate the gradients, which is not so often, and this will really speed. So basically, having model on a single node will really speed up the training due to the communication bottleneck. I will show numbers shortly. So that's why we went to Leonardo, which actually has 3,200 nodes. So this also means that we could take more nodes because Vega is actually quite occupied. And if we take a lot of nodes, this means that a lower percentage of total nodes on Leonardo than on Vega. And another nice feature is that it has 64 gigabytes of RAM per node. And this means that we actually managed to feed the model on a single node using the activation recomputation. I also provided here some nodes that we are using on our faculties cluster. I maybe need to give a special mention here to Grace Hopper nodes. So we have 2 Grace Hopper nodes, and each of them has Grace Hopper per 200 GPU, which has 96 gigabytes of RAM by itself, and it also has a unified GPU and CPU memory, so you can have a faster CPU offloading here as well. And the communication between nodes is again 400 gigabits per second. And another very powerful node here is B200, which contains 8 B200 cards, and it has 180 gigabytes of GPU VRAM per graphic card. And this means that even the 27 billion model can be fit on this node without any of these optimizations that I mentioned before. And the communication between GPUs on a node is also very fast. We were speaking about the terabytes per second now. And because of all of this, so only Leonardo is kind of suitable for large scale training. And how did we manage to split the model across multiple GPUs? Well, one way is to split it using the tensor parallelism. So this means that you actually split the linear layers in your models, and put each part of the layer on a separate GPU, and then they can process the data in parallel, and it reduces, of course, the GPU requirements from a single. So it reduces VRAM requirements from a single GPU. The next thing that I also mentioned before is activation recomputation. So the idea here is that instead of storing all the activations from the forward pass, you actually store the activation only for from the first, from before the multi-head attentions, and then you can recompute these inner activations of each attention layer when you're doing the backward pass. It slows down the training, so for around 60 to 40%, but yeah, it reduces the memory usage. And another thing that we use for scaling is, of course, data parallelism. And here is the idea that you put separate parts of your data to different GPUs, or in our case, to different nodes, because we had one model instance on each node. So you can then process data in parallel or at the different nodes. And at every gradient update, you just sync the gradients, and that's how you perform this update. Okay, as I mentioned, the speed comparison. So we actually benchmarked this these different node architectures. I need to mention here that this benchmark is quite old. So it was performed with NEMO 1.0 framework, and Leonardo was also not used optimally because it was so the model was split across two nodes. We did use activation recomputation here, but with activation recomputation, it could be used on a single node, and then if we would use the same amount of GPUs, the actually training would be faster using activation recomputation. But what I wanted to show here is that by actually keeping the model on a single node, so for example, the comparison here would be with our DGX A100 cluster, which has A100 node, which has only also 8 A100 GPUs. We can see that the training is actually faster than by splitting it across the two nodes, which is here case of Vega. And of course, yeah, Leonardo was faster because we did not have to use activation recomputation. And there is also these communication issues that I mentioned before. So for some reasons and some network instabilities, the training can fail due to nickel errors. This happened both on Vega and Leonardo. And the result is, of course, that you have then the idle time of your process. And yeah, of course, you are then occupying the cluster for no reason, and the cluster is also charging you the time that you use it. And by Murphy's law, this will of course happen when you are not monitoring. Now to go to the model evaluation part. So of course, after the training, we need also to evaluate our models. And here the LLMs are often compared on various benchmarks. So the most famous are, for example, MMLU, HelaSwag, Superglue, GSM 8K, or there is also a MED benchmark. So basically, people are inventing a lot of benchmarks. I even saw one where the models are asked to read the time out of the analog clock. But the problem with these benchmarks is that they cannot be really machine translated to Slovene, because even a small change in translation can cause a lot of problems. And as a result, we are lacking Slovene benchmarks. And the typical framework for evaluation on these mostly classification benchmarks is LM Evalve or LM evaluation harness from EULITER AI. and how this evaluation usually looks. So basically, the model is given some, for example, query. This can be question. This can be some premise or so on. So in this case, the input would be predator sit. And then it is given, for example, 4 options. So in this case, lions, humans, bunnies, grass. And basically, all of these options are put through the model, and then the log probabilities are extracted out of it. And so the one with the highest probability is chosen as the model's response. And basically, then the evaluation framework checks whether the response is correct. But what is the problem with such approach? Well, OpenAI just recently released a paper on why large language model hallucinate. And one problem is that we are also the way how we evaluated them. So here we can see the collection of most famous benchmarks, and this is taken from that paper. So most of them are binary grading. So whether the model was correct or not. So this is the way that I mentioned before. And the problem here is that we do not really test the model, or encourage the model to say, I don't know, if the model does not know the answer. And we are also not rewarding the model the negative points for answering wrongly instead of saying, I don't know. And this can lead to this, that the model are developed in a way that they always need to answer because they are kind of taught that answering something is better because you can still maybe guess the correct answer than saying, I don't know. And Slovene benchmarks that also follow this kind of classification tradition are superglue and natural language inference. These are published on Slowbench. Here I need to mention that test labels are not publicly available, so the evaluation here is a bit different. You cannot put the model into the same pipeline as you do with LMML. So that's why we've written a custom framework for evaluation of our models on these benchmarks. So basically, we prompt the model with the question, and then using also the guided decoding, we produce the answers, and then we need to upload the answers on this Slowbench website that is collection of these benchmarks. We also released the code for such for our framework. And and another alternative is we also have Slovenian LMML. So basically, some benchmarks that are included in LMML were machine translated by Alex Zagordic and his community. We then GPT-4 aligned them, but yeah, they're still problematic and are now part of the human annotation and refinement. Okay, but how to go from this classification suit to, let's say, actual real-world evaluation? And one very famous idea is LLM Arena. So here users can enter their prompts. So basically, you land on the arena, you can write anything in there, and you then get responses from 2 different models. And the model names are anonymized. So basically, you have model A, you have model B, and then you need to choose which response is better. So this can be either model A, model B, or you can have, you can say, let's say, neither of the responses is good, or it is a tie. And based on these user responses, then you have ELO scoring system like in chess that ranks the models. And this approach is actually good for evaluation and preference tuning. So once you have this user preference data, you can evaluate the models. Of course, you have this ELO rating, but you can also check why did your model lose to some other models, or if you can, for example, cluster the prompts by topics, you can find out on which topics your model is performing worse and so on. Of course, the danger here is that you will have troll users who will annotate in the wrong way, or for example, or we'll try to steer the model towards more, like for example, dangerous answers, and so on. And that's why it's important also to have some background automatic checking of such annotations. And yeah, when you have this clean data, then you can also use it for preference tuning. So this is for example, nice for the DPO method, or direct preference optimization, where the model is shown a good response and the bad response, and is trying to steer away from the bad response and towards the good response. I can also say that we recently released Slovenian LLM Arena, because current LLM arenas are mainly focused on English, because of course they have users who type in English. So the most famous from them is of course LMSys Arena. And yeah, with our Slovenian LLM Arena, we are actually asking the users to put in the prompts in Slovene. I think that we have now around 20 models on Arena. Of course, we have our GAMS models on there. We have Zlatorog, which is another Slovene model. We also included Euro LLM, and then the most successful open and commercial models. So we have Llama for Gemma Free, DeepSeek, GPT, Gemini. And here I need to really mention that kind of NVIDIA helped us with that, because we are hosting a lot of models through their NIM API, because we are their customer. We have access to that. Yeah, because we only have hardware for hosting, for example, GAMS models and Zlatorog. Okay, now to go to the data expansion and model improvement. So this is more like what the lessons learned so far and how are we improving on that. So as I mentioned before, from our national collection, we already received PDFs of the digital archive of our national libraries. So this is mostly old newspapers and books, because it's not copyright protected data. It contains around 9 billion words. But the problem is that these are PDFs. Of course, they also performed an OCR on that, but this OCR is kind of 20 years old, and it is not really up to the standards with the modern techniques. That's why we developed our own OCR pipeline, or let's say not so much as develop, or just like tested the modern architectures. And we found 3 different pipelines that actually work. So one is Marker, which is, so if anybody knows Marker, I need to say that we use it without LLM, because LLM are just slowing it down. And from all of this, the Marker is the worst performing, but it's actually the fastest. So kind of our approach is first use the Marker, and when it is not good enough, then use something better. And 2 models that are better are NanoNets. This is Quen specially tuned for the OCR. It is actually 3.5 billion model, and it's quite good enough, but it can produce artifacts, and it can start repeating itself. Luckily, such artifacts are usually quite long, because yeah, it is the problem of repetition. So it is quite easy to clean them. Just filter out 2 long lines or paragraphs that are repeating, and so on. And probably the best model was for OCR was Llama 4. But the problem here is that it is 400 billion model, so it is quite expensive to run. So for example, we had to run it on H100 GPUs on our faculty's cluster, or alternatively across 4 B200s. And that means that for large scale data, we used NanoNets. And another important resource of data was that we also expanded this academic Slovene corpus that I mentioned from before. So we went to, because it was up to the 2018, and we went to scrape the repositories of national universities. So we retrieved the PDFs of bachelor's, master's, and PhD theses, and now we also OCR them, and we collected around 2 billion words out of it. Next idea is to use machine translation, because there is a lot of high quality English corpora. One is of course Wikipedia, which has 5 billion words, while Slovenian has only 100 million. But another data set what was released recently is from NVIDIA. So the Nemotron pre-training data set is also high quality. But the problem here is that the best machine translators are still commercial models. So for example, DeepL, Gemini, GPT, but they are too expensive to use them on a large corpora. And the idea is maybe we can use open source models. So for example, EuroLLM is now quite efficient for translation. Our GAMS9B instruct can do a good job for English to Slovene, but there were still some problems with these translators, with these models that we noticed. And that's why we are now working on a specialized translator, and we are kind of finishing this work. So first we did SFT of GAMS9B instruct on translation data. So we really specialized it for translation. And then this was followed by the DPO using automatic metrics. So for example, we took Wikipedia, English Wikipedia, CC News, then Nemotron post-training dataset to also include marginal formatting. And then we just detected some simple errors that we noticed. For example, the wrong language in the output. So maybe the document was not translated, or the translation was truncated. It could do formatting errors and so on. And yeah, we kind of detected this, and using the DPO, we try to steer the model away from such errors. And we are also using Comet metric, which is a referenceless metric and can be used to improve the semantic similarity of translation. So now we are finishing this, and it's kind of showing promising results. So we hope we will have state-of-the-art translator really soon. Yeah, we are also improving the GAMS instruct data, as I mentioned before. So now we started to differentiating on task types, because to avoid repetition. So we separated open question answering, closed question answering. So with open question answering, the model is given a question from some topic and it needs to answer. In the closed question answering, the model is given a document and question based on this document and needs to answer. Then we have writing tasks. Of course, we can, so it's either write this mail, write this essay, rewrite this, correct this, and so on. Then we will also include math examples. We will kind of try to maybe get this from some national, from some national resources, and we will also include code examples. We already prepared this data set, so basically we checked a lot of public code data sets, then chose the best one of them. So we kind of were choosing based on the task type. So we have different task types. So yeah, I have this below. It's either writing code, rewriting code, explaining code, debugging, and so on. And then we translated this with Gemini 2.5 Flash. Kind of the Gemini is the best for the code translation. So for example, DeepL that could be good for another task is kind of problematic here because it also tends to translate keywords such as for, if, etc. Yeah, another improvement is that we are also now working on topic balancing for the open question answering part. So basically, my colleague really did a good categorization, and we identified 400 different topics. And now when we will generate the questions, we will explicitly ask the GPT or Gemini that to generate the instruction from this from a given topic. I also need to mention here NVIDIA Sovereign AI initiative. So we are now part of that as well. So idea is that each EU country could develop a sovereign AI model, and this is the help with NVIDIA. So they are kind of assisting us with their knowledge. They also released these Nemotron data sets that are really of high quality. And yeah, we actually already translated the sample of their SFT data set. We used our 27 billion model to translate them, so the translations are not that good, but yeah, they're decent enough. So, and the result was that this actually boosted our model's performance. So from using short responses. Now it really explains the decisions. It really kind of formats the responses in a nice way. And as a result, on our arena, it went from being behind, for example, Llama models to beating even GPT-4o models. So our latest GAMS model is now only behind Gemini 2.5 Pro on our LLM arena. And yeah, as I already mentioned before, we are now preparing our next iteration on a larger data scale in following 2 months. So yeah, this is in cooperation with NVIDIA. We plan to do around 100 to 150 billion tokens in continual pre-training and around 300,000 examples in SFT base. We will also work on context extension because now we have enough data. And then after this, we will also look to add reasoning and try to reduce the number of parameters using JetNemotron approach from NVIDIA. So we will maybe be able to reduce 9 billion models to 4 billion parameters and 27 billion to around 12 billion. Yeah, that's it from my side in terms of presentation. So thank you for your attention. Here is my email if somebody would like to contact me. I also listed yeah, the Hugging Face repository of our Center for Language Resources and Technologies. Here is the link to our poemo.c website, which was already mentioned before, and here is also the link to our Arena website. Okay.
Thank you very much for the presentation. It was very, very interesting. So the time for questions has come. If you have any question for the speaker, please, you can ask them now.
I see that one question is already in chat.
Yeah. The question is from Hreško Sebastian.
Yeah.
He asked this question. Did you consider generating synthetic data, text augmentation with LLM for pre-training?
Yes, that's an excellent question. So for pre-training phase, not. I'm still hoping that we can get more authentic data and that we can get a good enough data with the translation. So maybe this would be the better approach, because yeah, of course, with the synthetic generation, you can have all these problems that we faced in the SFT phase. So you can have hallucinations, you can have imbalance, and so on. So I would really like to first really exploit the authentic data.
Okay, thank you. Another question is about your presentation, and I would like to ask it as well. Would you be willing to share your presentation with us, for example, with me, and I would then forward it to our attendees?
Yeah, of course, I can do that, no problem.
Yeah, that's totally great. Thank you.
Can I have a question?
Of course, please go ahead.
I would like to ask you, you presented a table with computational times, and then there was a DP1 and DP high, and the time dropped radically. So what was that DP1 and DP high? Could you explain?
Yes.
And the second question, maybe you also mentioned that you got with synthetic data a lot of topics on photosynthesis. So did you ask GPT to write a random topic, or what was the prompt for the GPT? Thank you.
Okay, maybe I will answer the second question first, because it will be a shorter answer. Yeah, in our first stage, when we get this photosynthesis problem, we did not really ask it to generate from the specific topic. So I believe the prompt was somewhere in this way. So we are kind of your helpful assistant. You need to generate an instruction for an LLM. So yeah, so instruction that LLM can answer. So here are a few examples, and then we provided 8 examples from our starting data set, because I think around 200 and 300 examples were first written by hand. The prompt was not exactly like that. I don't know. I don't remember the exact phrasing, but yeah, it was in this line, but of course tuned a little bit, so it worked the best. Regarding this table, yeah, thank you. I forgot to explain that before. So there are various scenarios. One is, of course, using DP1. So this means data parallelism 1. So this really means that, for example, we train the model on only on these 2 nodes or only on this 1 node, and we are only using model parallelism. So this is tensor parallelism I mentioned before. But then when you're doing a large-scale training, you're also doing data parallelism. So as I mentioned before, different nodes then process different parts of the data. And for example, if you use 16 times as much nodes as now, so for example, for Leonardo, if you go from 2 to 32 nodes, the training time will approximately drop by the factor of 16, because of course you have 16 parallel instances. I can also explain why there is this high DP. Why are the numbers for Vega and Leonardo 16 and 32? We found out that we cannot go above 32 nodes on Leonardo. And that is actually not the problem of, for example, of our training framework, but it's actually a problem of Leonardo itself. Because when you working with the Slurm and on Leonardo, you have Singularity for container management and so on. When we start this job on 64 nodes, for instance, even the containers, even the container start is problematic, and the communication really drops. So that's why we could not go below 32 nodes. And by the way, we are not the only people that got stuck on 32 on Leonardo. On Vega, this number is even lower. So why here is 16 nodes? We could actually go to a larger amount as we did on Leonardo, but the problem is that Vega only has 60 nodes, so you have other users as well. And if you would go above 16, we would really have to wait for a long time. And also when you have these communication issues, we found out that there is no other solution that you identify the problematic node from the logs, and you then need to exclude this node from your training. So this means that even if you're using, for example, 16 nodes, you would have to exclude, for example, additional 4 or 5 nodes. So this is really then quite a significant percentage of the cluster. I hope I explained it enough.
Yes, thank you very much.
There are 2 more questions now in the chat section. Should I read it for you, or would you like to read it?
Yeah, I can read them. Problem.
Okay.
So how hard, easy do you find getting the time access to HPC like Vega or Leonardo? Okay, so there are different types of accesses. I would point you to the Euro HPC site where you can apply with your project. And then you, of course, have different types of projects. So one is benchmark access. For this is, I would say, not that hard to get. So basically, you need just to provide a description of what would you like to test on this HPC. But the problem with the benchmark is that you do not get a lot of GPU or node hours, because yeah, it's meant for benchmark. So this means that it's kind of your starting point. You realize how many resources will you need to scale your solution and so on. And then when you have that, you kind of need to ask for this, I think, large projects, or maybe they have even medium and so on. And for this, you need to kind of prepare a really well written project documentation. So you need to have a clear plan. What will you be doing and so on? What are your expected results? What is your contribution? And when you get the access, then of course you will also need to maybe learn to use HPC, because it's a bit different to just running on some local cluster or on local computer. Of course, you have Slurm behind. You need to do the environment management through Singularity and so on. But I would say that both Vega and Leonardo support teams are very responsive and helpful. So they will at least be able to help you with that. So question about how many researchers were working on this project. I would say less than OpenAI uses, just to clear one split of their data. So basically, we really have a small team because we are a university. In the core development team, there is myself and two other people. Then we also have, let's say, less than 5 people working on the data set. So yeah, apart from the data resources and the technical resources, another challenge is also human resources.
Can I have one more question? In the beginning, you mentioned that you needed to align English and Slovenian. Why did you need that?
It's not needed, but it helps. That's just one experiment that we tried, because there were some researchers that did this in SFT phase, actually. So they combined, for example, English instruction or English prompt and target language responses and so on. And yeah, we got kind of played around with the idea to try this in the first stage of pre-training, and it proved useful.
Okay, thank you.
Okay, are there any more questions to the speaker? If not, I'd like to thank you, Domen, for the great talk and very inspiring presentation on the Slovene model. It was really great and very interesting, fascinating. Thank you again. I would like to thank for all attendees for their questions, for being part of our series on LLMs and low resource languages. We in Slovak National Competence Center for HPC are still preparing new presentations. So please follow our social media, follow our site and website, and you will get notification about our future actions. Now, I would like to wish you a great rest of the day.